So maybe I can start, right? So I just continue what the discussion about Lagrangian Floer theory for torus fibers. So X via this compact keratotic manifold, and then I have a momentum map. So to this MR, which is actually isomorphic to the real of the real algebra, and then here P is a polytope, and this is actually defined by a collection of affine inequalities. So like Lj of U, it is actually by definition this Vj U minus lambda j. So it's positive. Okay. And Vj, okay. So now I take a point from interior of the polytope. Then this Lu is actually the inverse image of point U on this polytope, interior of the polytope. And this one is actually a free torus orbit, right? So this is a free torus orbit. And this is also easy to see that this is actually Lagrangian. And because this is a torus, so this is actually, you can identify it with a torus, therefore it has certainly spin structure. So it has many spin structures, but anyway, it has spin structure. So for example, if I consider just the easiest case like CP1, and then CP1 is certainly this circle, and then we have a S1 action over here, so therefore it fixes north pole and south pole, and then we have an orbit like this. And then the momentum map is somehow the height function, certainly up to a constant. I mean, momentum map is actually defined up to constant. And also, it depends how you define the generator of the vector field. So then maybe the image may be descaled. But anyway, basically it is a height function. And so we have here something like this. And then if you pick a point from the interior of this interval, and then you get this circle, small circle, or maybe great circle, and they are all Lagrangian. Right? And CP2, I cannot really draw a similar picture, but I have CP2, I don't know, somehow like this. And then this one is mapped to, say, this kind of triangle, and these three faces are corresponding to three lines here, right? Like Z1 is Z0 equal to 0, or Z1 equal to 0, or Z2 equal to 0. So you have three lines, and if you pick a point from the interior, somewhere, I don't know, somewhere here, and then you may have some torus here, right? So because the mapping is something like Z0, Z1, Z2 goes to sum of Zi square and maybe 1/2, and then z0 square, and z1 square, and z2 square. And then it is easy to see that the inverse image of one point is actually a torus orbit. Okay, so this is the picture. Polytope is sorry. Actually, I put it in a yeah, sorry. So this is in a, yeah, okay, just put it this way, okay. Say this way, thank you. So anyway, this is the example. And, okay. So now I want to consider the following. Maybe just this. So take beta from this H2 of x of value z and consider this moduli space this and then map it to so first we take J, which actually the complex structure of the toric manifold. So this is actually T invariant. And then certainly you have a torus action here, right? You have a map from this sigma d sigma and z0 z1 the zk a map to U. And then if you take an element, I don't know how to write it, G from the torus, and then G fixes this LU because it's an orbit, right? And then I consider the composition G composed with U. Sorry. Then we have this G, the same thing, sigma d sigma and Z0 zk goes to G composed with U and it goes to this, right? So this one actually is sent by grouped element G to this element. And so we have this torus action here. And certainly, yeah, the target is actually torus orbit. So we have a torus action here. This is a diagonal torus action here. And here also torus action here. And if you look at this, it is equivariant, right? Because aberration map of 0, aberration map I of element like sigma, d sigma, and Z0 to the zk going to U is equal to U of Zi, right? And then if you consider this Fi of G of the same thing, is certainly, because this is GU, so therefore it is G of U of Zi. And certainly this is actually mapped by G. So therefore, all these maps Fi are actually T equivariant. So this is T equivariant. And this is actually orbit, right? So let's consider a case of k equal to 0. And let's suppose that, yeah, everything is defined nicely. And then we have this m1 of beta going to this t. And sorry. Then maybe I just use w or something here. Sorry. Thank you. And so this. And then this is T equivariant, and this is certainly submersion, right? Because this is a T equivariant, so if we have one point here mapped to somewhere, and then I have a T action, and then it is submerged. So therefore, dimension of this m1 beta is at least dimension of T, and this is equal to n. Okay? So more precisely, somehow we have to use virtual technique in general. So then actually we have to take this virtual dimension of this modular space, but let's suppose that everything's okay. Then we get something. Because dimension of this m1 beta is equal to n plus mu beta. So this is the Maslow index plus 1 minus 3. So therefore this one is n plus mu beta minus 2. And because this is at least n, so therefore if it is at least n, right? So this means that this mu beta must be at least 2. So what I'm saying is if this is non-empty, so if it is empty, certainly you don't have anything, so therefore it is empty statement. But let's suppose that this is non-empty, and then you have one point here, and then map to here, and then it's submersive, and so on, so therefore you have this, right? So if this is non-empty, and then mu beta must be become good. Okay. Next, I come back to this diagram and try to see something. So, theorem is this. So this H1 of this LU with this lambda, in fact, lambda 0 part must be discussed a little bit more, carefully. But anyway, so this one is somehow contains this MC weak, this LU. Maybe at this moment, maybe this still. So this is a theorem. So I explained the construction of infinity algebra, and then talk about the set of Maurer-Cartan elements and potential functions. But I didn't say this set is empty or not. Last time I mentioned one thing, namely if the restriction map from X to LU induces a surjection, then under certain bulk deformation, actually, we can find certain Maurer-Cartan element. But here actually, this is a different statement, because in this case actually the restriction map is 0. But anyway, so we have this. So how we can see this? So let C be a one form. Sorry. I have to say this. So okay. Sorry. So this is a theorem. I will explain. Yes. This is a theorem. But maybe before that I have to say one more thing. So everything is T equivalent. So actually what I said is somehow then we have this map mk beta, right? But because everything is T equivariant, if I take here the invariant part of this, so I take an invariant part of this, then it must be mapped to invariant part of this. Right? Because this is T equivariant, everything T equivariant, the pullback is T equivariant, and push forward certainly also T equivariant. So therefore T invariant thing is actually mapped to T invariant thing, so therefore you must have this. But what we are considering is the torus. This is the torus, right? And torus acts on itself by multiplication. So somehow here what we get is some sort of parallel differential forms, or maybe differential forms which is invariant under translation, right? And so this one is actually isomorphic to harmonic forms. So this one is actually so what I want to say is this omega dot of Lu and take T. This is actually the harmonic forms. On Lu with respect to T invariant metric on Lu. So consider T invariant metric and then consider harmonic forms with respect to this metric. And then that is, in this case, nothing but the T invariant differential forms. So therefore, this one is identified with cohomology of the Lu, right? So therefore, this one is isomorphic to H1, H star of Lu. Okay? So therefore, in this situation, our operator MK beta restricts to such a space for harmonic forms. So maybe I just erase this. I wanted to keep, but so in this case, so X toric, Taylor manifold, and Lu is a torus fiber. Then our MK beta is actually a map from here to here without using any algebraic construction which I mentioned, canonical model. In general, we also have this, but this is after taking canonical model. But here, actually, just restrict this construction to the invariant part, you get this. So this one from here, actually, we have a infinity algebra somehow directly without using such algebraic constructions. Okay, so this is quite important things, and then I want to prove this. I somehow wanted to keep this, but maybe not. So this is I just erase it. Okay. So yes. So now I take Xi. So I just give the proof of the theorem. So let Xi be an element from H1 of this U with lambda 0. Okay. Maybe better to use lambda plus first. And then consider this mk of psi tensor k. How it is. And so, okay, so this mk beta of psi tensor k is equal to this F0 sweep and F1 star of C, Fk star of C. Okay? So this is a degree K form. So we have here mk plus 1 beta, and this one is a degree K form on these things, right? And now I consider here Lu is aberration map 0. And what is the dimension of the fiber? So dimension of fiber of F0. So I think I still have this, right? So in this case, I have this formula, but if this is actually k plus 1, and then this one is k plus 1, so therefore this is plus k, right? So this is a formula. So this one is actually n plus mu beta plus k minus 2 minus n. So therefore this one is equal to mu beta minus 2 plus k. Okay. So I have a k form here. K form, this k form here. And then want to push it out by this. And then this one is 0 if mu beta is strictly bigger than 2. Because if the mu beta is strictly than 2, and then the dimension fiber is more than k, but the k, we integrate along fiber of this k form. So therefore, if the dimension of fiber is more than k dimensional, and then it dies. So therefore, the only case which actually remain is the case that mu beta is equal to 2. Because mu beta is at least 2, and if mu beta is bigger than 2, it dies. So therefore, this one is only coming from contribution from mu beta equal to 2. Okay, so therefore, this mk beta of C tensor K is non-zero only when mu beta is equal to 2. So Xi is a one form. Xi is a one form. T invariant one form. Okay. And if mu beta is equal to 2, what happens? And then this is a K form, and the fiber of the dimension. So if then I think then degree of this F1 stack C wedge Fk stack C is just equal to K, and the dimension of the fiber of this F0 is equal to K, right? So therefore, this mk beta C tensor K is a T invariant function, zero form. So it's a T invariant function. But though this is a constant function, certainly, because Lu is a torus orbit, so therefore this is actually But in this case, actually 1 is a unit of this infinity algebra. So therefore, this one is in fact just proportional to the unit, right? So this mk psi tensor k is equal to the sum, yes, equal to the sum of beta, so mu beta is equal to 2. And, this is not really, okay, but anyway, so mk beta psi tensor k and t to the this. So this is a function. This is actually a constant function. So therefore, if you add them up, and this is also a constant function. On LU with values in this lambda 0. Okay? So actually lambda plus. But anyway, so this. So therefore, yeah, this one is proportional to the unit. So therefore, any H1 of LU, this lambda plus, is in fact contains this MC weak of this. Maybe Q. Okay, so this is the conclusion. Half of the conclusion here. So still I need to consider constant part, but this is mostly. And then, for how about this constant part, right? So if B is a H1 of this LU with C, so you can think of it as just a T invariant one form, and then you can think of it as a flat connection. So actually maybe if you just consider this H1 of LU and C over 2 pi square root minus 1 of Z, then this B actually corresponds to certain flat line bundles on this LU. So it's just a flat line bundle, and may not be unitary because it's just here just a different form with complex coefficients, not purely imaginary things. So therefore, may not be unitary. But anyway, so we have this. And then we can actually do the following. So what is this MKB of this? And so this is a sum of mk beta of C1 ck and to the T beta omega. So that's the same thing, but we may just twist it by this. So namely, so beta is a map from D, sorry, not the disk. This is a connected boundary going to this X of LU. So therefore, we can have a class. So this is I don't know, maybe some W here. If this is represented by this, and then this one is represented by W this with D beta, D sigma, right? So you have a loop, or you have a loop on LU. And then because B, you can associate some Floer line bundle, and then you can take a holonomy of this Floer line bundle along this boundary loop. So this rho B is actually a pi 1 of this LU to C. This is actually a holonomy, monodromy maybe. Okay. So in this way, actually, you can deform the infinity structures, and then do the whole business. And then you also get this. So this is actually the idea by Shelfin-Cho. And so we can also deform our infinity structures by using the classical part of the cohomology of degree 1. Okay. In general, certainly, somehow you can also think of this. But certainly in this case, actually everything is defined on the cohomology, so therefore it's very easy to understand. Otherwise, somehow, but still you can do this, yes. Because Floer line bundle is there, and then you can twist construction by Floer line bundles. And yes, so on the cohomology level, you can do this. So combine with this, and then for any classical part of the cohomology here, you just do the same thing. I mean, what I mean the following. So, for instance, if I denote it by say B0 here, and B0 here, and everywhere, right? B0 here, okay, and then we can consider some construction here, but we can also put here B0 here, right? And then after the same argument, we can also put B0 here and everything, right? So here I have B0 here, B0 here, and B0 here. So therefore, I have this B0 plus psi, and B0 is this classical part of this cohomology of degree 1, and psi is a cohomology with lambda plus coefficient in degree 1. So if you add them up, actually you can get everything. So therefore you get this. But it may be better to say that this should be mod out by 2 pi square root minus z. So maybe theorem prime. So in fact, if we consider this H1 of LU, and this lambda 0, 2 pi square root minus 1z, is actually contains this MC weak of LU. Now I just remove this tilde, because they are actually, this is exactly in this case a gauge equivalence relation. So then I can just throw it. Okay. So before really discussing some examples, I just want to tell you general story a little bit more. So the potential function of this LU is this. In fact, yeah, more precisely, I have to put here B0, and then here I have to put B plus tensor K. Something like this. Maybe this may be better. Yes. Yes. Something like this. And so now B is an element in H1 of LU with, at the beginning I just still use this lambda 0 things. Okay. Maybe I need to be a little bit more careful, but anyway, so this. And then this one is actually written as some linear combination of these things. Okay? So what is EI? Actually, I just took an integral basis of the lattice M. This lattice M is identified with the first cohomology of the torus. And because LU is a torus orbit, so therefore the first cohomology of the torus and first cohomology of the Lagrangian LU actually canonically identified, right? Because you can identify T and LU up to translation, but this translation is trivially acting on this. So therefore, there is a canonical isomorphism with H1TZ and H1LUZ. Okay? So this E1, En actually can be considered as a basis of this. Okay? So this is actually canonical isomorphic to H1 of torus. And this one is actually isomorphic to M. And here I have a basis. So therefore you have this kind of thing. So this xi, actually this lambda 0. Okay, so I just write in this way. And then consider the following things. Somehow this is just a formal computation, but just try to do this. Okay, so in general we have to do this, but let's consider the following things: Mk and B tensor K. So this one is equal to Mk and B, okay? And this one is Mk and sigma xi ei tensor sigma xi ei, right? So I just want to differentiate with respect to xi. And then xi appear here, 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 so several places. And so if after that I take a value at point B, and then this one is equal to this is actually sum of Mk of Ei, B, right? And then sum them up. And this is exactly the definition of MB1 of EI. So here I have EI, BBB, and BEI, BBB, and this, right? And I already erased, but what I wrote MKB of Xi1, Xk is actually the whole sum of this Mk plus L0 plus Lk, and here I put L0 many B and Xi1 and L1 many B and so on, and Xk, and then Lk many of this, right? So we consider such things. So arbitrary number of b may be put in front of psi1 or between psi I plus 1 or after psi k, and that is exactly this distance. So therefore, this is M1b of EI. Okay. So if we call the B is a critical point, of this function, if this because potential function is after a function on H1, so I have a basis and I have a coordinate, and then I just consider the direction derivative in all directions, and if all vanishes, and then we call it a critical point. Okay. And so if B is a critical point, what happens? So M1B, then M1B of EI is equal to 0 for any basis element in H1. So namely, M1B is 0 on this H1 of LU. Okay. And now we use the following fact. So cohomology of LU, maybe even complex coefficient, yeah, is generated by H1 as an C algebra. Maybe I have to also put the unit, but so unit is there, and then unit and this part generated by H1. Okay. So this is one thing. And so if you consider this M2 of C1 tensor C2, then this one is somehow, I need some sign here, but this one is C1 with C2 plus higher order terms. So as I said, this M00 is equal to 0, and M10 is differential D, but M20 is actually defined by using the moduli space of bordered holomorphic maps, but representing class 0, that is constant maps. So you have a constant map. So in that case, actually, you have this M and beta equal to 0, right? And here I take 3, 2 plus 1, so this is 3. And such a thing is certainly identified as a constant. So therefore, this is actually, we can identify it with LU itself, right? Because 3 points on the boundary of the disk, is actually equivalent under PSL2R. So therefore, this one is. And then here you have a map, LU times LU. So this is just a diagonal embedding in this case. And then here, this is also identity map. So here you take a product, right? So first part and second part, you take a product, and then pull back by a diagonal map. And then what you get here is that exterior product of these two blocks. So like this. and then push out. So because this is identity, so therefore this is against this. Okay? And this is a case that beta equal to 0, so symplectic area 0. And the other classes, the symplectic area is positive. So therefore you have a higher order term like this. Okay? So therefore, if you consider this M2 things, so maybe I also need to put B here, but it doesn't really matter. So M2B here, and then so this one is not really algebra. I need to really change the sign. Yeah. So last time I said that infinity structure, if you have a DGA, you can cook up infinity algebra, but you need to change the sign, right? So you have a usual product, and here you have M2 operator, and then you have to change some sign in certain way. So therefore, this is not exactly this, but there is a way to convert this M2 operator to the product. And so this is actually also generated by H1 over U, this. Okay. Now, I said that B, if B is a weak Martin element, and then what I said, one is just M1B composed with M1B is equal to 0, so this is the first thing. And second one is M1B and M2B satisfy the Leibniz, right? So namely, I have this M2B, and M1B and M2B and Xc1 tensor Xc2 plus minus plus M2B over M1B Xc1 tensor Xc2 plus minus M2B of Xc1 M1B Xc2 is equal to 0. So this is what I said, this Leibniz imbalances. And so if Xc1, Xc2 are elementing H1, then M1B of Xc1 is equal to 0 because of this, right? So because of this. So therefore this one dies, and this also dies. So therefore the product of the two elements from H1 also die by this. So now you have such a thing. We know that this product die, and then take another H1 element from H1, and then consider product with this one with C3, and then do the same computation, because this one already died, and so therefore, yeah, you can just keep doing this. And so because using this and this, so using these two properties, actually we can show that this M1B is in fact 0. So what does it mean? So this means the following. So this is actually an important thing. So if B is a critical point of this PO LU, then M1B is equal to 0. So therefore, if you consider the cohomology of with respect to this M1B, so this is a differential, and this one is certainly isomorphic to the cohomology of this, because differential is trivial. And so this one is in fact this bottommost type Lagrangian Floer theory. Okay. So maybe better to erase this. Like this. So maybe I just this. So this one is HF. In this case, I still use the lambda 0. But this thing is, yeah, this one dies, and so it is. So then we can also consider, so here I have H star of this LU, lambda 0, going to this H star of LU, lambda 0. Actually, this is a lambda 0 linear map. And so therefore, we can extend it to this. To this. Like this. And this is nothing but H star of LU with lambda coefficient. So therefore, we can also show that not only this, but also lambda, vanishes. Okay. So then the conclusion is HF LU B of LU B lambda 0 is isomorphic to the cohomology of LU lambda 0 as a lambda 0 module, and HF LU B and LU B lambda is isomorphic to H star of LU with lambda as lambda module or lambda vector space. Okay, so this is it. And in fact, it is if and not if. So if it is not a critical point, we can also show that the Floer homology is actually trivial. So in fact, so B is from H1, where U is lambda 0. So B is a critical point of P of LU. If and only if this HF of this LUB is equal to 0. Okay. Okay, so this is one of the things. So far, I consider potential function of torus fiber. And in fact, there is another potential function, the potential function of the toric manifold. But in order to, but maybe before that, maybe I just, sorry, non-zero, sorry, non-zero. Non-zero. Yes. But this statement says that if it's not a critical point, then this vanishes. So if this is the case, this one is isomorphic to the cohomology of the manifold, cohomology of the Lagrangian. But otherwise, it just dies. So statement, maybe you're right. So this is one statement, and if it is non-zero, then in such a case, actually this is isomorphic to the ordinary cohomology as a module. Okay. So here I said that this is as module. How about the ring structure? And this is again an observation by Cherfin-Cho. So actually we computed this first derivative potential function. But if you consider second derivative potential function, what do you get? Then what you get is actually M2B of EI EJ plus M2B of EJ and EI. So this is just a similar computation as I explained here. You just write down this potential function as a sum of all mk, b, tensor k, and then differentiate in xi, then xj, and then you differentiate two places, and then you differentiate first maybe xi in the right, in the left of the EJ, or maybe you may differentiate EI, which is the right of the another thing. So therefore you have this. So from here, actually you may say that this Floer homology of this LUB with a product using these things is actually a Clifford algebra. Associated with the second derivative of potential function. Okay, so this is also quite nice. Okay. So later I talk about critical point of potential function of a toric manifold, and here it's the critical point of Lagrangian torus fiber, and certainly they are closely related, but not. Yeah, you shouldn't really confuse these terminologies. So therefore, I spend some time to explain this. Okay. Okay. So I have this. Okay. So now I think I don't really use this. Okay. So we are interested in the class beta whose mass of index is 2. And so somehow we have to study whole mass of 2 disks. But there are some basic, rather basic things. So there are so-called maybe basic disks, or maybe meridian disks. So what does it mean? So actually that maybe I will explain bit later. So you have compact toric manifold here, and then there may be finite many, actually there are finite many torus fibers where they admit some critical point. Most of them doesn't have any critical point, but some of them have critical points. And then count the number of solutions here, 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 and then add them up. What you get is the sum of Betti number with the toric manifold. So this is one thing I may explain. So each of them may have finite many solutions. And then if you add them up, and then you get sum of Betti numbers. So mass of 2 disks. Okay. So then maybe I just like a P. P is actually some convex polytope. I don't know how does it look like, but anyway, P is here. Then we consider its facet, I mean codimension 1 face. So maybe I just write D1P and D2P, DDMP. Because they are actually, so DIP, DJP is actually point in P, so that this Lj of U is equal to Z. Right? So this J is just a facet. And so then I have a manifold X here, and here I have pi. And so therefore we can have dj pi inverse of djp. So this is actually divisor. This is a toric divisor. So for instance, when we consider this P1, then the image is just like this. And so this is a P, this is P, and then this is a boundary, codimension 1 boundary, and this corresponds to just one point, like a north pole, and the other one may be south pole. So these two are divisors, and point is divided on last surface, I mean curve, and then it is invariant under torus action, right? So therefore it's a toric divisor. And in the case of CP2, and then, I don't know, this one may be corresponding to some axis, and this one may be another axis, and then the other one may be mapped to some axis, like this. So this is actually, Z1, Z0 equal to 0, or Z1 equal to 0, or Z2 equal to 0. So all of them are toric divisors. And this sort of things. And so now I take point here, U. And then look at some facet. Then there is a meridian type disks. So how can I write it? Okay. So okay. So I have X and remove all toric divisors di, dk, which is different from j. Just remove all the toric divisors away from d1, dj, and then this one is actually isomorphic to C star then C here. And this is actually I don't know. Maybe this is not good. This is not good. Sorry. This is not good. So maybe we have to write C times C star to the power n minus 1. Yes. Yes. So in this case, if you remove the yellow one, then what you get is C, complex plane, right? So n equal to 1, and then you don't have anything, so therefore this is complex plane here, or maybe complex plane there. And in this case, if you remove this, say, blue and orange things, and then I have only this yellow one here. And so therefore, this one is, so if you remove this, sorry. So, I don't know how to say. So if you remove this blue one, then certainly you have C times C, right? And then you remove one of the axes. So that is one of the axes, so therefore this may be 0 times C or something, right? And this is actually certainly the C star times C. Right? So this one is always written in this way, because it's a toric manifold, and then you have this. But now LU is certainly here. Because LU is on the interior of polytope, and this toric divisor actually on the boundary of this. So therefore, because U is the interior, certainly they are away from all toric divisors. And so therefore, this one is away from here. And this is a torus orbit. So therefore, this one corresponds to some S1 times A1, and S1 times A2, and S1 times AN, something like this, okay? So this one is in this complex plane, and this one is this punctured plane. And then certainly we can see disk here, that is this disk. So therefore, instead of this, we may consider disk of radius A1, and then maybe some point. So this is a basic disk. Corresponding to associate with this dj. Okay. So for each j, you have such a disk, and this one has mass of index 2 because yes. So here is one thing. So you have X, toric manifold. Then you consider all the divisors like D1, Dm. So this is the union of all toric divisors. And this one is actually Poincare, is a Poincare dual, is a is the Poincare dual of the first term class of X. And this one is again, you can see as follows. So here you have C star, or N, is contained in this C, contained in this X, right? In this X. And so here we can consider the following thing, like a Z1 over DZ1, DZ1 over Z1 with Zn over Dzn. This is actually a holomorphic N form on this C star to N, non-vanishing holomorphic N form on this torus. And if you look at this, you can see that this N form has a pole along each dj of order 1, right? And so, but has poles of order 1 along d1 dn, right? So you change the basis, and then you can also change this description. But anyway, you can see this. So therefore, this one is so-called section of canonical bundle, and dual of canonical bundle, and first term class of canonical bundle is actually minus of first term of the tangent bundle. So this one, the Poincare dual, is just a negative of the sum of d1 to dm, because this is pole of order 1. But first term class of the tangent bundle, so this one is tangent bundle, it's negative of that, so therefore this one is a Poincare dual class of this. And in fact, for this LU, actually this d1 dm is also a Poincare dual of the Maslov class. So Maslov class is some relative version of first term class, and in this case actually we can also see this. Argument maybe similar argument can also tell you this. And so if you consider such a meridian disk, a basic disk, so let's denote by beta j H2x LU of D as the class represented by the basic disk associated with this dj, and then mu of beta j is somehow the intersection number of beta j disk and this dj things. Sorry, maybe I have to say this. Okay. Yes, dk. Okay. You know how disk look like, and then this disk is away from other decays. And so therefore, if j and k are distinct, and then this is equal to 0, and this is equal to 1, if j equal to k, because this is a point, the origin times origin, and then this one is disk. So therefore, this one is equal to 1 or 0. So if j is equal to k, and j is not equal to k, right? Sorry. This is equal to the sum of this, right? Because this is the sum of them. So I have to add k equal to 1 to n. Sorry. And 2 times of this. This 2 times of this. Because as I said, this oriented torus is oriented, so therefore all the massive indices are even. And so this and this one, but this one is equal to 1 or 0 if j equal to k, and j is not equal to k, right? So therefore this is just equal to 2. So therefore this one is mass of index 2. So this is mass of 2 disks. And this mass of 2 disks is quite nice. So these basic disks are regular. Regular means the linearization of Cauchy-Riemann equation is actually surjective. The reason is somehow, we have some kind of complex torus action, so it can move in any directions. So therefore, so this is actually follow from equivariance. Actually, this one actually follow from this torus actions. So if you heard of the Gromf-Witten theory of genus 0, and then for homogeneous case, homogeneous variety, if you have a rational curve inside there, then this one is actually regular because homogeneity actually tells you the whole H1 of the linearization operator actually 0. So anyway, so this is quite similar. So this is okay. And Cho and O also show that this, so any disks are regular. This is disks. This is not bordered stable. So for border stable maps, it is not the case. But for holomorphic disks, actually they also show this. But what we need is basically for these basic disks, and that is actually quite easy to see. And also they also describe everything, but okay. So anyway, so this is one. And then what do we want to say? Okay. So now I consider the following. So let X, J, omega is a compact toric Fano manifold. Fano condition means that the canonical bundle, maybe the dual of the canonical bundle is actually ample. Or first term class of tangent bundle is represented by a Kähler form. Kähler form, but it is integral class, so therefore integral Kähler form. So this is the Fano condition. So this in particular says that if you have A, it's actually the class H2 of xz represented by a rational curve. Not necessarily rational. And then first term class of Tn represented by A is actually positive. Not necessarily rational, but what we need is only rational. So, okay. Yes. So any disk, actually here, maybe any disk. So you have such a disk, and then has positive mass of index. Because this one is actually intersection number with this guy. But because if it is a disk, then you have only one component. This one component disk certainly cannot stay in these divisors, because these divisors on the boundary of polytope, but U is the interior of the polytope, so therefore the image cannot be contained in any toric divisors, right? So then the intersection number with holomorphic curve with complex variety must be positive, so therefore this is positive. Okay? But here I'm considering not a disk, but rational curve. But if it is Fano, then actually any Chan number must be positive. Okay? So border stable map consists, maybe a border stable map consists of a holomorphic disk and rational curves and holomorphic disk, we have this Maslov index, and each holomorphic disk has Maslov index at least 2. And rational curves, the first Chan class, first Chan number is actually positive. So therefore, the contribution to Maslov index of the border stable map is actually bigger than or equal to 2. What does it mean? So you may have this holomorphic disk, and then because of this, actually any holomorphic disk has positive Maslov index. But now this one is actually orientable, right? Then this Maslov index must be even. So therefore at least 2. And then there may be other one, like maybe other one coming here. Each of them actually have certain positive Maslov indices. And then you may have sphere bubbles somewhere. Maybe some of them do not have. And then these spheres contribute to the Maslov index of the whole thing. But the contribution is actually twice of the first Chan number. So therefore, if we have this, and then this must contribute twice of first Chan number, but because Fano condition, it is positive. So therefore, each of them has at least contribution by 2. Okay? So, but remember that for computing this M star EB, and B is actually H1, yeah, we only need beta with mu beta is equal to 2. So therefore, it must be simple one. So if you have more component, and then it doesn't satisfy this. So it is just one simple disk. Okay? And then such a thing is actually only basic disks. So for no case, those beta are exactly basic classes. So we only need to study this. So then there is a chance to compute potential function. Okay. So I have this beta j, okay, and then want to compute this potential function. Okay. Yes. So yes. Okay. So beta j is a class from D. Sorry. Beta j is not. Beta j is represented by something like this. Maybe I may write wj. So this one is unique up to polar suction. So this is unique up to polar suction. Because I erased, but maybe I just write it this. Here you have C, and then here you have C star, C star, and then here I consider this disk, and then point, right? So this is a disk. No other things. And then here, actually, we have some ambiguity by rotating the disk. But this rotation is somehow, just a circle action here. And then there are points. But so you have Lagrangian here. So they are this. I mean this the boundary of D of A1 times point is actually like this Lagrangian. And these choices also, unique up to the torus action. You can change any point to other point by circle action here, and then so therefore this is actually unique up to torus action. And therefore the dimension is actually also expected. So this one. And then next I want to tell you what is this thing. Maybe this one is H1 of LU of Z, right? Maybe better to I still have something. Okay, I still have this. Okay, this one. Okay. Sorry. Maybe better to write this way. So you have this H2 of X and LU going to this H1 of LU and Z, and this one is actually isomorphic to N, and this one is in fact isomorphic to Z. Yeah? And so, it's okay? Not okay? Possibly. Okay, then I just finish this. So here I have a basis E, J. J is 1 to M. And then here actually Vj mapping to this. So actually this beta j is this one. And the boundary beta j is this one. So this one is actually beta j class, and this one is a boundary beta j class. And so this is actually corresponding to the map I described before. Okay, then maybe I just take a break, and then later I just keep computing this.